Yeah, comes on everyone. Start off. Hope everyone has gone through the notes. Last class we did some really good ones, especially the transverse voltage one. Where are the rest? Hmm. Okay. Why so many people are missing today? Hmm. Okay, let's go ahead with this thing. So the next thing is Kirchhoff's junction law. Others do keep your cams on. So again, this stuff is exactly the same thing, that we did in capacitors. So there we said like the net charge flowing through a node is 0. Here we will say the net current entering a node is 0. So let's say if current I1 is coming here, I2 is going this way, I3 is going here, and I4 is going here. So the net current entering I1 plus I4 must be equal to I2 plus I3. Right? Or you can simply say the total current that is flowing in is equal to 0. Now, how to do this thing? Let's say this is R1, this is R2, this is R3. Remember this story? We did the same thing in capacitors. So V1, V2, V3, and X. Let this current be I1, let this current be I3, and let this current be I2. Since the total current entering the node is 0, I1 plus I2 plus I3 is equal to 0. And what is I1? Potential difference by resistance. So current in a resistor is potential difference across the resistor by resistance. So you're taking I1 from V1 to X. That means you're assuming V1 is greater than X. So V1 minus X by resistance R1. I2 is going from V2 to X. So V2 minus X by R2. V3 minus X by R3. If you remember in capacitor, it used to be Q1 plus Q2 plus Q3. And there the formula was Q into CV. So we used to write C1 into V1 minus X, C2 into V2 minus X. I hope you can see the resemblance. All clear with this? And then we solve this, we get X ka value, and then we can put it there, and then you'll get the answers. So just to show you the steps. There, if you see, we did the same thing here. So these were the steps. Choose a point with zero potential, find the potential of other nodes, and then apply junction law. So I will put this there. It is exactly the same thing, only the formula is different. Page 92, capacitors. This is your junction law. All clear with this? Let's see a question on this. This is 2V, this is V, this is R, this is R, and this is 2R. You can clearly see nothing is in series, nothing in parallel, no Wheatstone bridge, no nodal analysis, no symmetry, nothing. Find current in each branch. If you remember, there are total 5 techniques that we have: series parallel, nodal analysis, Wheatstone bridge, symmetry. In symmetry, we again have multiple things: infinite ladder, infinite grid, axial symmetry, bisector symmetry, diagonal symmetry, cube symmetry. So, and then the fifth one is your junction law and loop law. So first we are seeing the junction law. Find the current in each branch. Try. I'll give you 2 minutes. In case you want to see the steps here, you can just read through this once, this red ones. You can refer to this problem, exact same stuff. Have a look at this for a minute. Okay, let's see the question now. Step one, start with zero. Normally, you take the negative terminal of any battery as zero. And luckily, if you take this as zero, this is also zero, this is also zero. Current in towards, yeah, right, Samik. Okay, let's see. Step one, start with anything as zero. I will take this guy as zero. This will be zero. This is zero. If this is zero, this point will be 2V because the battery will have a potential difference of 2V. You took negative terminal as zero, the other guy is 2V. This guy is V and this guy is X. Let the currents be I1, I2, I3. I'll always take towards the node, okay? Matlab, there'll be no confusion. Like if something is reverse, you'll get a negative sign, so don't worry about it. I1 plus I2 plus I3 is 0. So I1 will be 2V minus X by 2R. 0 minus X. So I'm assuming I2 is going from 0 to X. So 0 is greater. The signs will take care of themselves. And this would be V minus X by R is equal to 0. R goes off. This will be V minus X by 2 minus X plus V minus X is equal to 0. So this is 2V is equal to 5X by 2. X is equal to 4V by 5. You're done. So I1 will be 2V minus X. That's 5 to 10 minus 4, 6, 3V by 5R. So plus sign. My direction is right. I2 will be minus 4V by 5R. My direction is wrong. It's not going up. It is coming down. I3 is V by 5R. My direction is right. All got this? Easy stuff? Yeah. That's how you handle this. If you remember, we did something quite similar in capacitor. So let's see a few more on this. Now, we will slowly bump up the level. You'll see, like, what kind of questions can be framed, like which we didn't do some in capacitors. Let's do this one. Let's say this question, if you remember, we did this thing in heat transfer. We did this in viscosity also. Let's say this is R, this is 2R, and this is 3R. This point ka voltage is 3V. Let's call this point A. Let's call this thing O. Let's call this thing B is 2 volt, and let's call this thing C, which is V. So it's a Y-shaped branch. Find potential at O and the current in each branch. So actually in this thing, the circuit, there is a battery and there is all circuit here. I'm not showing you all that. I'm just showing a part of the circuit. Find potential at O and find current in each branch. This is a very good question. You should put a star for this because this can be asked in 4 different chapters. I didn't ask you this in capacitors. So, first time where you saw this, heat transfer. ये question याद है? 3T0, 2T0, T0, LKA, 2LK. Find temperature at D and heat current in each rod. The second time you saw this question was actually the first time you saw this question was in viscosity. Look at this thing. A Y-shaped pipe, pressure is 3P0, P0, 2P0. Idea was the same. Even there, we treated like a resistor and we solved it. I can do the same thing in capacitors also. I can do the same thing in current also. That's where it becomes a really good question because you can ask in 4 different chapters. Let's get this. Same story. Let the current be I1, I2, I3. Yeah, you get it. Okay. Potential at the center. If you got potential at O, you'll get everything. So just tell me that. So I think answer is not really that great. Yeah, Samyak, both of you got the same thing. So try. I'll give another 30, 40 seconds. Okay, let's see. Here, luckily, potentials are already given, so there's nothing for you to do there. So let this current be I1, let this current be I2, let this current be I3. Now, this is what I'm saying, see, keep this thing simple. Don't assume like, okay, current yahan se ja raha hai, wahi se aa raha hai. Like, you just keep it simple, like, like I1, I2, I3 all going towards it, which, is not going to happen. So someone will be negative. Now that, why I keep doing this every time? Because I have seen this, when you're in exam hall, right? And when you're already in the 10 state and you're doing a lot of things, people start, you're wasting time thinking, okay, current is coming from here, current is going here. Just an example, look at this question. Everyone is sure current is coming from 3 volt because that is greater. Everyone is sure current is going to voltage V because that is smaller. But the confusion comes, is the current coming from 2V or the current going to 2V? That we don't know, isn't it? That's the confusion you'll have in the exam. So when you have that confusion, right, you will get stuck. You will start thinking, and that will waste 30 to 40 seconds. More than time, it will actually consume your mental bandwidth. Sabko lagta hai, when you're in exam, you get, you have 2 types of energy, a physical energy and a mental energy. You start exhausting your mental energy. Getting it? So when you're stressed out, your mental energy drains faster. So if you keep your number of decisions smaller, you can conserve your mental energy. Right? And that is the main thing, Did you ever do this thing? You wanted to order something from Swiggy or Blink, or Zomato. You open that and you're just scrolling restaurants for 20 minutes, right? And after some time, you'll get so pissed off and you're like, shit, yeah, I don't want to just order anything. Matlab, you're just searching for 25 minutes. In that time, the food could have come, but you have no idea which one to order. Kabhi hua? So you're draining your mental energy. You getting it? So I have this problem. So what I do, when I decide I want to order something, first I don't open my phone. First I'll tell myself, what do you want to eat? Now, there will be barely 3 to 4 options you'll think of. Pizza order करने हैं नहीं यार boring है. इतना बड़ा कौन खाते? बिरयानी खाने हैं, वो तो last 2 days back I ate. You know, and then say what do you noodles? हाँ, noodles try करते. Now see you're clear. Now you open the restaurant and you know what to eat. You have to decrease your decisions. Getting it? That's just about the food. And the same thing, your seniors also did this. 1 week before the advanced exam, the instructions I gave and they followed was simple. I think I told you this. Every day morning, wake up at the same time you're going to wake up on the day of the exam. Eat the same breakfast, eat the same lunch, eat the same dinner. Literally, everything you're going to do on that Sunday morning, repeat it 7 days like a rehearsal. Because on the day of the exam, you don't want to get up in the morning and then you're suddenly having a problem going to the bathroom. Right? If that's going to happen, and you will panic, right? Matlab, hota hai, yaar, you got 10, 15 minutes late, you got into the cab, now you're getting tense like, oh, will I reach the time on center? Recently, I read somewhere NEET may they throwed people out because they're 1 minute late. You'll start remembering every damn nonsense. You're draining yourself out. So keep your decision simple. So when you're studying, also you should do the same thing. Let the method be a little longer, but can I replicate the same method even when I'm under pressure? So now go back to our notes and see every time that I teach you, that is where I always teach you from with that mindset. The method might be a little longer, might look little, weird, but you can replicate it. Every time you can replicate it. That's why see, every time when I teach you, I always give you steps to solve. When I taught you Kirchhoff's law, steps to solve, right? Forget about Kirchhoff's law. When we started laws of motion, if you guys remember, even when we did, the free body diagrams, it started from there. Where is this? There. Rigid body constraints. There. Steps to draw a free body diagram. Choose your system, draw this, draw this, draw this. And then we came to solving problems. Again, I wrote steps. Choose your system, draw FBD, choose your coordinate system. And where I took the inspiration from this? Coding. When you write a code, this is what you actually do. This is how you tell a computer how to start solving a particular problem or write instructions. If you just write any nonsense instructions without connecting them, the whole code will get confusing after some point of time. Right? So it's important. So start learning that way. It will become more easy for you and you'll be able to actually, compartmentalize them, everything. So yeah, so keep it simple. Let the current always go to a node. So there. Now, these are the things which you should learn. So let's not take that to be 0 because that 0 is looking confusing. I'll call it X. So yeah, then you're done. So V minus X by 3R, 2V minus X by 2R. Think about what I said. Continue working on that. It will just take you maybe 2 to 3 months to revise yourself. You will really start thinking in different way. You'll be able to connect a lot of stuff. So when you do this, people got the answer. I'll just write it down. 26 V by 11. So you can substitute there and you'll get I1, I2, I3. Clear with this? Yeah, I like this question because it comes in multiple places. So yeah, I think I did tell you this before also. Next one. All these are junction law problems, and you can see we did same problems in capacitors also. There is no diagonal symmetry here. That would make your life easy. Let's not do that. So get this thing. Find R equivalent. You know how to find the R equivalent. Let the current be I from the battery. So V by I ka ratio is R equivalent. Others who didn't get 26 by 11, please check your answers one. And oh yeah, just look at your answer. You got more than 7V. So, why, yeah, it's okay to get wrong answers, but understand when it's a blunder. Hmm. Again, this is why I keep saying, revise, revise, revise. Yeah, I hope you remember this. This was the exact questions. C, 2C, 3CC. See, exact same thing. I just capacitance in place of a resistor in place of a capacitor. Uh, this you have to solve. It's not that, it's not tough also. It's not easy also. It's a little solving involved. Try, I'll give you a minute. I'll do one thing for you. Wait. So we have to start with the voltages, right? Let this be 0. Let this be V, and let this be X, and let this be Y. If you find X and Y, your job is done. Then you know the story here. We'll say I1, I2, I3. Then we will say this is I4, I5, and I6. And then we will say current here is I1 plus I4. So R equivalent is V by I1 plus I4. So your job was to find X and Y, and your job was to find I1 and I4, and you're done. Go ahead. That's the whole process. Now solve. It's important you solve on your own. If you don't solve a question till the end, till you get an answer, what happens in the exam, right? That's why some of your calculations are so slow. There is some person I was talking recently, and the kid was saying, "Sir, I use calculator to do calculations because I feel it's a waste of time. I will use my head to think and use calculator to solve." I said, idea was good, but do they allow calculators in the advanced exam? No, then don't do it. No, it's as simple as that, right? Suppose if copying was actually allowed in the final exam and you can take answers from outside, why don't you do it? That was the most easiest thing to do, isn't it? We don't do it because it is not allowed. Yeah, फिर भी नीट में चल जाता है, but JEE advanced is still a little difficult so far, I guess. Someone got something. Yeah. Show you. So we are finding X, I1 plus I2 plus I3 is equal to 0. V minus X by R, phi minus X by R, 0 minus X by 2R. R goes off. V minus X plus Y minus X by 2 is equal to 0. This is 5x by 2 minus y is equal to v. That's your equation 1. मेरे परम इतना अच्छा आंसर नहीं आएगा. हाँ अन्विता, that is right, I guess. And then when you do for y, uh, I4 plus I5 plus I6 is 0. This is v minus v by 3r plus Mm, x minus y by r plus 0 minus y by r is equal to 0. This would be v by 3 y 2y 3 to 6 7 y 3 minus x is equal to equation 2. Got the same equations? So people are saying when you do this, uh, y ka value is 11v by 29, x ka value is 16v by 29. If you take this and solve this, I think this will turn out to be, mm, yeah, right. It's a 29 r by 11, 29 r by 19. So substitute I1, I4 and get it. I think same answer आया था ना capacitance में भी 29 C by 19. Hmm. I'm not solving it. So check your equations. If you got the equations, you're right. I know you guys are expert in solving two simultaneous equations, so I trust you. Clear with this. Now let me show you a proper advanced question, how they'll frame this thing in advance. Any doubt so far, please ask me. Now, I keep telling you, right? Questions, right? Some are tough, which are easy to solve. Some are lengthy, some are tough. So these are the two categories there. Some questions, right? If you see, they have more of a shock factor. You see the question, you feel like, what the hell? And but then if you can calm down and see, maybe it is easy to solve. Mm, yeah. This is our circuit. So the currents are given here. You can clearly see each branch has current 1 ampere, 1 ampere, 1 ampere, 1 ampere. So four currents are coming in. So this guy is going out, going out, going out, and going out. I'll just mark this in green. So this guy is coming in, this guy is coming in, this guy is coming in, and this guy is coming in. All are 1 ampere. And they're asking, find the current in the branch AB. Yeah, let's get that. You can take all resistances 1 ohm. It actually doesn't matter, but yeah, makes your life little easy. Let's do this. It's actually difficult. If you have it on a pen and paper, it would have been nice. But think. It's don't, like I said, now you see the question, you feel like, what the hell? So when I saw this question for the first time, you know what? I was like, okay. And then I saw the numbers 111. And I was trying to guess, okay, without solving, I was trying to guess. I said, maybe the answer will be 0, or maybe 2, or 4, 8, 16. I was expecting something like a multiples of 2. I was just guessing. And then I looked at the answer and it was like a slap on my face. I said, okay, let's not do any random guessing. Shut up and solve the problem. So I started doing it. Yeah, try. Think, I'll give it 2 minutes. Don't worry about the answer. Think whatever we can, how to figure out. Just a hint, we are using junction law. Anyone is confused with the question or something? Ask. Someone got something? Near area. Told you na. 0, 2, 4, 1. Those are good numbers. I was expecting something like that, and I felt like I got a slap. Okay. Listen, I'll help you with this. Or should I leave it this as a homework? You want to try, and next time we can discuss. I'll leave it as a homework. It's a worthy question. If you figure it out, it'll take a minute to solve. So I'll just say that much. So try it as a homework. We'll do it next class. अच्छा क्वेश्चन था. You should get some time to do it. It is unfair for me to ask you to solve in 2 minutes. नहीं कुछ folding नहीं करना है. Let's see one more. We will not solve this whole question, but I just want you to write the main steps and just the equations will do. I showed you this before though. Find RAB. All distances are R. Just get me the equations. So let's see how will you simplify this. Take 2 minutes. And then I'll show you the main equations and then you will get it. Yeah, right, Arya. So idea तो वही है. So try, get the equations. And if you're thinking, oh, what the hell is this? You're not revising the notes. This was the same example I gave in capacitors, page 103. When I was teaching you diagonal symmetry. इसमें actually, if you see, na, these two are in series and this is in parallel. So you can actually compress that thing. It makes your life a little easier there. Try, write your equations, guys. You just get the equation sufficient. Not much you can solve. Okay, let's see. 3R. I don't think you'll get such a good answer though. See, because after the initial point, nothing is in series parallel there. So if you look at this junction here, this whole triangle here, that R and R are in series, and this will be 2R by 3. Where is this? This whole section also will be 2R by 3. Then what you can do here, you can remove this and you can say this was 2R by 3. This is 2R by 3. There. Now you can't actually do anything. There's no symmetry here. So then you will say, okay, this is let the battery be connected here. Let this be V, let this be 0, let this be X. Now see, whatever current flows in this 2R by 3, same current flows in this 2R by 3. So this potential difference must be equal to this potential difference. There's a diagonal symmetry. So if that is X, then this will be V minus X. If this is y, then this will be v minus y. Remember this? There, that's your node. So there are actually only two different variables you have, x and y. And then we will say let the current be I1, I2, and I3. And here the current will be I4, I5, I6, I7. So there are four currents at y, and nothing wrong with that. So for x, we will take I1 plus I2 plus I3 is 0. V minus x by 2r by 3. Y minus x by r. V minus y minus x by r is equal to 0. You do for y, that will be I4 plus I5 plus I6 plus I7 is 0. V minus y by r plus x minus y by r plus v minus y by r. V minus x minus y by r. If you solve them, you'll get x and you will get y. And you will say R equivalent is nothing but V by I1 plus I4. That's the current flowing in this branch. So solvency, I'm not sure. I don't think you'll get 3R, but maybe, who knows? I will leave it to you. Clear with this? Any doubts on the equation, please ask me with that part. So this is how you handle diagonal symmetries. These are little more, brute force problems. If they decide to ask you something more, like if they don't want to ask you symmetries, this is the thing they can ask you, because this thing has symmetry, but still you have to do your work. Lengthy one. Clear with this? Let me something more different, like it's more smart. They have to do more conceptually. There. So all batteries are 1 volt. All resistors are 1 ohm. Let this point be A and let this point be B. Find the difference between VA and VB. Previous one, 10R by 19. Okay. Utsa is saying 10R by 19. You can all verify. Thank you, Utsa, for helping the lazy teacher in the lazy class. but others do verify. Okay, this thing, right, is a very interesting thing. Listen to this logic, what I said. If you try to do the individual, right, you will get it, but there are hell lot of variables. Listen to my idea here. Not only this circuit, you take any circuit, and if you cut it into two pieces, listen to this argument. If you cut any circuit into two pieces, can I say the total current crossing this line in one direction must be zero? What do you guys think about that statement? If you take a circuit and if you cut it into two, matlab, forget about a line, huh? You can even do something like this. And if you say the total current crossing this curve, right, whatever is the current crossing the curve in one direction must be zero. I'll tell you why. Listen. Do you remember this? If a battery sends a current I, the current has to come back to the battery, right? Because the batteries are simply pumps, isn't it? Batteries do not create any charge. If a current I goes from a battery, it has to come back to the battery. Is that clear? That means this current is somehow forming a loop, isn't it? Yeah, it is splitting and it is doing everything. It is forming a loop. So if you cut a loop, the current crossing the loop must be always zero. The current going in one direction must be equal to the current going back because the current has to go back to the battery. Is that logic making sense? Because if you just forget about the wires and if you just see battery ka perspective, every current that comes out of the battery has to go back to the battery. That means this current is forming a loop. And whenever you cut a loop, the current crossing and current going must be always equal. So we'll apply junction law, but this time we'll apply junction law at a larger scale. This is what we do. Listen to this argument. So this green line which is there, so I'm applying junction law on a line. The total current crossing the line must be zero. Now, there are one or two ways you can argue this. So can I say like this? This line is simply nothing but 1, 2, 3, 4, 5. So these 5 nodes, what is the total current entering the node? 0. So when I draw this line, so this line is considering all the 5 nodes, isn't it? If current through each node is 0, then the total current in 5 nodes is 0. Therefore, the total current in the green line is 0. Is that statement making sense? Right? But I think you can also say like this. Current leaving a battery comes back to the battery, forming a loop. Therefore, net current crossing the line must be 0. Actually, net current crossing any line is 0. You can argue like this also. And then you're done. So let's start from here. So let this point be 0. Nodal analysis, this is 1, this is 2, this is 3, and this is 4. Let this be x because I don't know what is that. But if this is x, then this point is x plus 1, this point is x plus 2, this point is x plus 3, and this point is x plus 4. Any doubts on the nodes ka potentials, everyone? So reality mein there is only one variable x. Then we will say the current crossing the node, let this be I1, let this be I2, let this be I3, let this be I4, let this be I5, let this be I6, I7, I8, I9. There are total 9 currents which are crossing this line. So instead of writing nodal analysis for each node, I'm writing nodal analysis for the whole thing. So that is I1 plus I2 plus I3. I4, I5, I6, I7, I8, I9 is 0. Yeah, what is I1? X plus 4 minus 4 by 1. What is I2? X plus 3 minus 4 by 1. I3, X plus 3 minus 3 by 1. Yeah, you got the thing you saw. Now you can how it is forming. X plus 2 minus 3 by 1. X plus 2 minus 2 by 1. X plus 1 minus 2 by 1. X plus 1, 1 by 1. X minus 1 by 1. X by 0. Do you have 9 terms? 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. Yeah, so just add them up. That would be X. You'll get 9X. You have a 1 here, 1 here, 1 here. That is 4 is equal to 0. So we get X is equal to 4 by 9. In this, where is point A? This X plus 2 is point A. This 0 was B. So VA minus VB is simply X plus 2. X is 4 by 9. That's 22 by 9. Make sense? Chalo, let me tell you this another way. So no, if you just take this node, right? Current coming here and current come here will cancel. So when you add all the nodes, right, actually you'll get the same thing. But did you get this idea here? So if I just remove this part of the circuit, all the currents coming out of the battery must go back to the battery. So that means the net current crossing the green line must be 0. That is the whole essence. Like you can apply nodal analysis not at a single node, but you can take 10 nodes together and apply nodal analysis for all of them. And it should still work because nodal analysis simply says entering is equal to leaving. Is this making sense? Now, if you do that way, now it looks easy, right? Now manageable, matlab, but frankly, you should have seen this before. Now, if you see this before, it becomes easy in the exam. All got this. Any doubts on this? So there. So this one, this is a standard one. The homework question, give it a try. All these are standard models if you see. So if you ask me in this one, 16th one and 18th one are the really good ones in junction law. Remaining all stuff is random. I mean the general ones. Great. That's a bit about the junction law. The next thing is Kirchhoff's voltage law. This is a very powerful thing when we have multiple different elements. After this, we're going to do that only. RC circuits. What happens if we keep a resistor and a capacitor together? You're going to combine different elements. Kirchhoff's voltage law. You know the story here. I'll just copy it from here. It's exactly the same stuff. Nothing changes. That's the best part. You really don't learn anything that new. Like you are just repeating stuff. The only difference here will be the sign convention. If you have a resistor, how will you write the sign convention? Current always flows from higher to lower. So if you go in the direction of the current, potential will drop minus IR. If you go opposite to the current, potential will increase plus IR. That's the only thing there. Please have a look at this once. Yeah, voltage law is the loop law. Kirchhoff's voltage law, Kirchhoff's junction law. So potential difference between 2 points is a sum of potential difference across the elements in any path between the 2 points. This is the sign convention. If you go in the battery from negative to positive, sign convention is simple. If you go from plus to minus, potential will decrease. If you go from negative to plus, potential will increase. Clear with this? Now we will not solve all big questions on this. The main thing is writing equations. So I'll give you one question example. Let's just write the equations. If you got the equations, your job's done. I'll make this unnecessarily complicated because we're not going to solve only the equations. This is the voltage R1, R2, R3. The steps are the same. Choose the current, let it divide, all that stuff. R7, R8. So I'll give you the currents for convenience. Let's say the battery is giving current I. So current I comes here. This will be I1. Then this current will be I minus I1. Then this current will be I2. Then this current will be I minus I1 minus I2. This current will be I3. Then this current will be I minus I1 minus I2 minus I3. I1, I2 will combine. This will be I1 plus I2. I1, I2, I3 will combine. This will be I1 plus I2 plus I3. And then the whole current comes back. So do whatever you want. The current has to come back to the battery. Now, what I want you to do, write the equation in this loop, this loop, this loop, and write one equation from the battery going from the top and then coming back. Meaning, I want you to go to the battery, go R1, R2, R3, and come back. Understood? We did something similar in capacitors also. Can you write the equations? Just get the equations, like, so that we are sure your convention signs are important. The left loop, middle loop, right loop, one loop going through the battery, R1, R2, R3. And also write one equation going from A to B. One equation from A to B. Yeah, any way you can write. First, get the four loops. Remember the convention. If you go with the current in a resistor, potential will drop because current always flows from higher to lower. If you go opposite to the current, potential will rise. How do you know you have to take like this? This is what I wrote. You can write any directions you want, any variables you want. I wrote this so that we'll get same equations. Okay, let's see. See whether you got the same equations. Starting point won't matter. Maybe the terms will get, just pushed left, right. So I'll start from here. I'm going up. So I'm going through this guy. I'm going with the current. So minus I1 R1. Then I'm coming down. I'm going opposite to the current. So that is I2 R7. Then I'm going this way, again opposite to R4, plus I minus I1 R4. I came back to the same point, 0. Anyone not play with the thing? You messed up the sign. You think this is wrong? Please ask me. Like, this is important. The most common mistake is people mess up the sign, nothing much. I'll start from here. You can start from anywhere. I'm starting from there. I'm going to the right, minus I1 plus I2 R2. Then I'm coming down here, R8 may. R8, when I'm coming down, I'm going opposite to I3, I3 into R8. I'm going left in R5, so that's I minus I1 minus I2 R5. Then I'm going up with I2. If I go in the direction of the current, it should drop. So minus I2 R7, I came back 0. Check the middle loop. Then I'm writing the right loop. V minus I1 R1 minus I1 plus I2 R2 minus I1 plus I2 plus I3 R3 equal to 0. You're done. And you want to go from A to B? You can go anywhere. So I will just go like this. You can go in any other direction. So VA minus I1 minus I2. I started from VA. I went through R5. I drop because I'm going with the current. Minus I3 R8. I dropped and I reached VB. So if you just want to write between 2 points, this is how you write. Because see, when you complete a loop, you come back to the same point, then this also become VA. So VA gets cancelled. That's why we get 0. Are you getting why we get a 0? Because if you come back to the same point, the initial and the final point become same. This is how you write an equation between any 2 points. You start from VA, your voltage is VA. You went through R5, it decreased. You went through R8, it decreased. Where did you reach? You reached VB. You can also write like this. If you go up, VA minus I2 R7 minus I1 plus I2 R2 is equal to VB. This is also right. Both will give you the same answer. It doesn't matter how you go from A to B. Potential is a state function. It does not depend on the path. Both the equations are right. You could have taken any path. Please have a look at all the equations, any sign, anything you're not convinced, something looks weird. No, wait, I had a big mistake. No? I wrote this is the big loop actually. I didn't write for the right loop. Yeah, that's a big loop, I'm sorry. Let me write the right loop again. I'll start from point B. I'll go to the right side. Minus I1 plus I2 plus I3 R3. Then I go opposite to R6. So plus, yeah, these are pretty big. Then I go up minus I3 R8 and then I come back to B. That's 0. Please check your equations. All clear? So Kirchhoff's loop law is right, is especially useful when you're going from one point to some random point through multiple batteries and multiple resistors. Junction law becomes difficult sometimes. So let's see a question on this. That's it. If you understood that writing equations, your Kirchhoff's law is good. So we have two circuits like this. This is point A and this is point B. Find VA minus VB. This is a good question, right? Standard model, meaning you will see this in different forms. If it is a CET question, right, they'll ask you find the current in this 2 ohms. That will be a CET question. That could be even a decent mains and bits question also. But let's get this. Let's see how will you handle this. Find VA minus VB. There are 3 batteries. Okay, did you guys notice something? The most important catch in the question is this. Again, going back to that argument, I keep telling you this every time. A battery does not produce charge. If a current I comes from the battery, it has to go back to the battery. Okay, now with that in the mind, let's talk about what would happen. Let's say this battery is giving current I. As the current I is coming here, imagine some current I goes here, small I. That means the remaining current I minus I will go here, and this current will be I minus I here. That means you're getting only I minus I back in the battery. Can you see the problem there? So if the current tries to go in the 4 ohm ka branch, there is no way this current can come back to the battery again. Same way, I can also argue here, if this is I1, I1, I1 minus I. If I say this guy is giving current I2, this is I2, this is I2, then this current will become I2 plus I because it's coming from here, and that is also wrong. So the only way to solve this problem is what? If small I is 0, current cannot go through that 4 volt ka battery because there is no way for the current to come back. Are you clear with this? So it's a very important thing, remember. So someone gives you two circuits and they just randomly connect with one thing, current will never flow through that one wire. Because if the current goes from here to here, there is no way the current can come back to the battery. Are you clear with this? That was the main catch in the question. Yeah, if they put a wire here, then it's a different game. Current can come back, then current will flow. But there's no wire there. So that was the main idea here. That's what I said. It's a pretty good CT or a bits question. Like find the current in 4 volt battery. 0. You can see and tell the answer. So let's just put that down. So current leaving the battery has to come back to the battery. Because batteries do not create charge. They are just neutral. Must come back to battery. So how much current you sent? You sent I1 and how much current is coming back? I1 minus I. So therefore I1 must be equal to I1 minus I. This is only possible I is 0. Therefore, no current flows in the connecting branch. You don't have a path to come back. All clear with this? And once you got that, then you can simply solve the question by saying both the circuits are independent of each other. Then we will say, so current is flowing I1 here. So this is I1, this is I1. We can clearly see I1 voltage is 10 and the resistance is 10. I gave good numbers. That is 1 ampere. So here the current is I2, this is I2, this is I2. So I2 is also 1 ampere. Perfect. You want to go from A to B? I'll go like this. Remember in this branch, current is 0. Then I can go like this. This is how I'm traveling from A to B. I'll start from A, VA. I'm going through the battery, negative to positive. So I will get extra voltage plus 10. Then I'm going through the 3 ohms minus I1 into 3. Then I'm going through the 2 ohms, which is I into 2. I is 0. Then I'm going through the battery again, plus 4. Then I'm going through 3 ohms, I2 into 3. Then I'm going through the battery again, 6. Then I reached VB. This term would be 0. This would be VA plus 10. I1 is 3. This would be 4 minus 3 plus 6 is VB. That would be 6, 4, 10, 10, 20, 20 minus 6, 14. So VA minus VB is equal to minus 14. Clear how we did this? So the main catch in the question was that the junction won't work. If you don't realize that, then it becomes really difficult to figure out from there. Right, Utsa? Any doubts on this? And it's a pretty good CET question. What is the current in that connecting branch? People will do all stunts. You just have to tell yourself current coming from battery is equal to the current entering the battery. And you're done. All clear? Do have a look at this. Any doubts so far? Do ask me. It's a good one there. Let's just do one more and then I'll give you a break. You remember this problem. Hmm, we have done this in capacitors. Now we can solve this whole thing. These are the currents. Huh? I'll just mark them in red. So this is your I1. This was your I2. The question is find I1 minus I2. Get them up. You remember this thing, right? Maze circuits. You need to find a path where the resistor is the only one and remaining all are batteries. Do one thing. Take a break. Come back by 9:45. We'll continue from there. Take a break and then we can do this. No issue. Any doubt so far? Chalo, come back by 9:45 then. Yeah, let's solve this. Hope everyone got the answer. Chalo, cams on everyone. So what is the answer for this? Let's just magnify this a bit. So for I1, we will go like this, this. Yeah. So you're going in the battery plus V, plus V, plus V, minus V, plus V, and minus V. And you're going through only one resistor. So there are four plus V's and this thing. So 4V minus 2V minus I1R is equal to 0. I1 is equal to 2V by R, and voltage is given as a 10, and this is 4, so that's 5 amperes. Perfect. Now, when I2 is going in this direction, you can see actually even there are multiple resistors. You can treat this whole thing as one branch. That would be R by 2. This would be 5R by 2. So I can treat that whole section as one branch. So I will go this way. I'll go this way. I'll follow this red ka path. I'll come this way. Check. So then this would be minus I2, 5R by 2, plus V, plus V, and you're done. You came back only two batteries. So I2 will be 4V by 5R. That's 40. R was how much? 4. That's 20. That's 2 ampere. And the question was I1 minus I2. So that's 3 ampere. Yep. Right on that. All clear with this. Do look at the paths. You could have actually, the red one, right? You could have gone like this also. That would have worked. But you just have to find the path. Any path would still give you the same answer. This is how you solve maze circuits. All clear with this? Great. Any doubts on this? Anyone not convinced with anything here? Please ask me. Let's see one more. Let's say we have a battery, resistor, and a capacitor. Let's say this is a 3 volt. This is 2 ohms. And let's say this is 2 farad capacitor. The charge on this capacitor, Q is equal to T square by 2. This is minus Q. So the charge on the capacitor is changing with time. This is point A, this is point B. Find VA minus VB at t is equal to 2 seconds. These are another good ones. So you have a battery, resistor, capacitor, everything. The Kirchhoff's law doesn't care what element it is. It will follow the rules. If you go from positive to negative, I will drop. You go from negative to positive, I'll increase. You can give any element you want. You can put an AC circuit, you can keep an inductor, you can give anything. Let's get this. Okay, let's see. So first thing, how do we handle this? If you remember, there is actually current in the circuit. How do I know that? Because charge is changing with time. Because I know I is equal to dq by dt. The charge on the capacitor is not constant. It is changing with time. So there is a current in the circuit. So you have to be careful. There is nothing compulsory like, charge on a capacitor must be constant. So that will be I is equal to dt. So at t is equal to 2 seconds, the current is 2 amperes. So this is changing with time, and the charge on the capacitor is also 2 coulombs. Great. Now you write the Kirchhoff's law. You're starting from A, you're going through the battery, +3. You're going through the resistor in the direction of current, minus I into R. Then you're going from positive to negative plate. So minus Q by C is equal to VB. E or none. I is 2, that is 2, that is minus 4. Q is also 2, Farad is also 2, is VB. So VA minus VB will be 2. That's 5 minus 3. Right, Akansha? Clear with that? So the main thing is to figure out, since the charge is changing, there is a current. That's it. Most people don't figure out like, oh, there is a current in the circuit. Please check your signs. Easy one. This is a really good question. Not too tough, right? But when you have all the three elements, how do you figure it out? They won't give the current, but they'll expect you to figure out the current from the changing charge. So that's how they can play this game. All clear with this? Great. So that is a little bit about Kirchhoff's junction law, circuits, and all that stuff. If you see, we did questions which we didn't do in capacitors. So when you're solving circuits, you should always treat capacitors and resistors circuits together as one combination, right? Because in any one chapter, you'll not find all the models. I did half of them in capacitors. I did half of them in resistors. So next time when you revise capacitors, make sure you're revising both the notes for capacitors, for the circuits. Clear? The next thing. This is another important part, RC circuits. What happens if we keep a resistance and a capacitor together? Now, before jumping into that, we need to discuss something about a steady state. Do you guys remember what's a steady state? We already heard this term 2 times. In heat transfer, conduction, steady state. What is steady state there? Current will always flow. The heat inflow is equal to heat outflow. This was a discussion about steady state. The property does not change with time, right? For different positions can have different values. See, even I wrote a current example there. The current in the nodes and the voltages in the branches will be equal. So I'll just copy paste this. You can see, right, how much I keep going back. Every class we go at least once. And some parts, so literally we can copy and you will not even feel like, oh, the chapter is different. This is the steady state. So in circuits, when you say it is a steady state, it simply means the voltage and the charges on the capacitors does not change with time. Now, in the previous case, if you see, this was actually a non-steady state. The charge was not constant. The current was not constant. This is a non-steady state. Clear with this? So if something changes with time, it's not steady. Great. So what happens in a steady state? Let's see how the capacitor behaves in a steady state. Now in a steady state, you said the charges and the voltages will remain same. Charge on a capacitor is constant. So if you take a capacitor, and if you say the charge is Q and minus Q and the current is I, in steady state, I is equal to dq by dt and Q is constant is 0. There, that is the main catch in the question. When someone says the circuit is in steady state, that means all the capacitors will have zero current, meaning they have charge. The charges become constant. Current and capacitor is zero and they do have a constant charge. The capacitor is full. That's why it's not letting any more charge flow through this. That is the main thing. So how does this work? So at t is equal to 0, when you put a capacitor, an empty capacitor behaves like a wire. So if you have an empty capacitor, you can treat this like a wire at t is equal to 0. So it's like a zero resistance. Because think about it. Since initially you're empty, the first electron which is coming there, it will not have anyone to resist, isn't it? Think of like this. Let's say you have an empty school bus. You are the first person to get inside. Will there be any resistance? Or let's say when you get into an aeroplane, you are the first person to get inside. Is there anyone in front of you to block you? No, right? You just go straight and sit where you want. But imagine you're the second person. There is a probability, right, that the guy in front of you, right, might have seat number 7 and your seat is something 25. And he's just standing there in the corridor and putting a bag. So you do slow down a bit. There is a probability. But let's say you are the 70th passenger. I'm pretty sure there'll be someone in front of you blocking. That means as the plane gets fuller and fuller, there is a good chance that you will get blocked. The same way, if you have an empty capacitor, there is no one there. So the first electron which is coming, there's no one to stop you. You have zero resistance. Is that making sense? Something of that sort. So, and imagine all the seats in the plane are full and you're that extra passenger. Do you think they'll let you in? Oh, you don't have a seat. Come, take the pilot seat. We'll throw the pilot out. So that's not going to happen. They won't let you into the plane the same way. So at T infinity, when your capacitor is full, it won't let any charge come inside. It says, like, boss, you're full. Just there's no place for you. So at T infinity, if you keep a capacitor connected to a battery for a long time, it does get fully charged. This is what we also call as a steady state. They have different words, T infinity, long time, steady state, all these things mean the same thing. So the capacitor becomes full. This aeroplane example was good. I just made it up. So capacitor becomes like an open circuit. It does not let any current flow through. So you can treat this as an infinite resistance. Remember, this is only at 0 and infinity. What happens in the middle? That's a story for later. So a capacitor at infinity behaves like an open circuit. These are called steady state circuits. Again, whatever I'm teaching here, similar stuff, again, you will see in a chapter called electromagnetic induction, EMI. There we have something called LR circuits. The theory will look quite similar. But any doubts on this page, please ask me. So at T0, capacitor you can replace with a wire. At T infinity, you can put this thing. So let me show you an example and then I'll ask you a few more on this. So they would ask you questions of this sort. Let's say you have a battery, we have a resistor, we have a resistor, we have a resistor, and we have a capacitor. So we got a battery, we got a resistor, and we got a capacitor. So the question would be like this. Let the current be I. Find I at T0 and T infinity. So listen to this question like, so these are two different questions. You want to try? Give it a try. I'll show you, but think you on whatever you understood, you give it a try. I think that would be good. I'll keep it as a question only. Try for 2 minutes and I'll show you. Remember at T0, you can replace the capacitor and make it a wire. So just replace the capacitor, put a wire. At T infinity, current won't flow through the capacitor. So with that as a logic, try to figure out. T0 रे हो गया? Nah, be careful ना. T0 में capacitor becomes a wire. Draw the circuit. Always draw the circuit. T0, T infinity, draw the small circuit, you'll understand. Try. Whatever you think, do it. It's okay to get a wrong answer. Param, get me the charge also. 3V by 4R 4 नहीं आएगा रे. You goofed up, I guess. Check there. Samyak, that is right. Okay, let's see. So first I'll draw for T0. T0, the circuit will look like this. It becomes a wire. So you just draw like this. So this is 2R, this is R, this is R, and this is G. This though you know how to do. These two are in parallel, 2R by 3 plus R, 5R by 3. R equivalent is 5R by 3. Current will be 3V by 5R. They can even ask you find the current in the capacitor. So you can do that. You can split the current. This will be 2I by 3 and this is I by 3. I didn't ask you, but could be. So at T0, that is how it would behave. At T infinity, your capacitor is full. Now remember, capacitor is still there. It just doesn't let the current flow through this. So don't literally remove it because you won't be able to find the charge then. So this is a better way of doing it. You still keep it there. So this is V, and we will say this capacitor will have some charge plus Q and minus Q. It is full. And the current in this branch, small I, is 0. So all the current is flowing only to these two resistors. And this is R and this is R. Yeah, so we can clearly see I is equal to V by 2R because current only flows through them. And then we will, how do you find the charge? We will apply the loop law. We'll apply the Kirchhoff's loop law here. We will go from here. minus I into R, minus I into 2R, you're going from positive to negative, minus Q by C. Then you're going opposite to the current, plus I into R, you came back to the capacitor. There, that's how you use Kirchhoff's law. If you have multiple elements, Kirchhoff's law is the best. So we will apply Kirchhoff's law in that loop. What is small I? 0. Minus Q by C, and what is I? V by 2. Therefore, the charge on the capacitor is CV by 2. Understood how to find the charges? Keep the capacitor, let the charge be Q. Current in that branch is 0. Find the current in the other branches, then apply just one loop law passing through the capacitor. You'll get your charge. All clear with this logic?
But can we
Par.
also say that like the change in V, like initially it was V by 2R, then it became uh, 0. So CV major change आया, that is the charge that is accumulated.
Mm-hmm. That logic, it won't work. Like initially, what was the potential difference?
So initially V ही है
It
पहले
was
तो
zero, right? It was zero current.
अच्छा initially 0.
तो वही हो गया ना, because here you're lucky because these two are in parallel, right?
हाँ.
What if it was not in parallel, or maybe what if there are multiple resistors or something like that? Yeah, in this question your logic was right. So I'm not sure, Master. If the circuit was different, maybe it need not be necessary.
Okay.
Yeah, if you're sure there's a resistor in parallel, सोचो अगर यहाँ पे भी एक बैटरी है तो can you still say that? Then problem आएगा ना. Yeah.
Okay.
Yeah, but it was not a wrong logic though. I'm not sure. Maybe for something else, it might be a problem. So let's do this. If you got this, I think you all understood this steady state stuff. So this is C, this is 2C, this is R, this is R, and this is R. Let's put a switch here. So there is a switch here. This was I. Find I at t is equal to 0. Same question. And just copy the questions. Yeah, let's get this. So recently I was teaching a class offline. So I wrote something like this and I was trying to copy paste it from the board. I was looking at the board and I was smiling at myself. I said, yeah, I do dumb things. Sure, let's give it a try. Yeah, so you guys got the previous one. Let's get this one also. Okay, let's see. Yeah, Param, currents are right. Kanksha, currents are right. Samyak, currents are right. Charges also look right, I guess. Charges I need to see. I don't remember the answer. Right, Trishi. This is a Trishi. Just look at the second answer. What did you type? Look at this. This is a very interesting, they can ask you a simple question like this. Find R equivalent before and after closing the switch for a long time. That is also a very good question. So how does your circuit look at T0? At T0, your capacitors are open. So you can are wires basically. So you can just replace them with wires. This is how the circuit looks. So you can clearly see if this point is A, this point is also A, this is B, this is also B. So in reality, there are only two nodes, A and B, and you can clearly see all three are in parallel. So R equivalent is R by 3. Current will be 3V by hash. If you wait till infinity, the capacitors will get full. Now be careful. There is a charge there. I don't know how much. So let it be Q2. This is minus Q2. I don't even know whether the charge is same. So I'll just take Q1 and minus Q1. Let the signs take care of it. The current in the capacitors will be zero, zero. That much I know. So all the current will flow through this guy, and this guy. So basically, current is flowing. Follow the red line. It doesn't pass through the capacitors. Perfect. So what is R equivalent here? 3R. This itself is a good question. So at T0, all the resistors are in parallel. At T infinity, all the resistors are in series. So R equivalent will change. So they can ask you find the ratio of R equivalent at infinity and zero. It will be a good integer question. 9 would be the answer. So current would be V by 3R. Great. How do we find the charge? That is, most people get the resistance part and current part. The moment they ask for charge, people start getting confused. Some people do get it. But remember, if you use your junction law, it makes your life easy. So apply one loop law here, one loop law here. You just have to go through the capacitor. So I will go through the Q1 there. So I'm going anti-clockwise. You go in any direction. So I'll go from minus Q1. So that is Q1 by C minus I into R minus I into R. So I'm going through this is equal to 0. So Q1 is 2 CV by 3. Yeah, you're done. And what about the other guy? I'll go in that loop. So Q2 by 2C minus IR is equal to 0. Q2 is 4 CV by 3. I think some you got the same thing. Do check your answers. The charge is not 0. They are full, right? That's why charge is not flowing through them. If they're full, that means they have a potential difference. If there's a charge, there should be a potential difference. Please have a look at this. This is a good one. Finding charge on a capacitor is a little tricky there. All clear with this? I'll give you one more like this. This is V, this is R, this is R, this is 2R, this is 2V, and this is capacitance. Find charge on the capacitor in steady state. Steady state meaning infinity. That it looks big and scary. It is actually manageable. Give it a try. Okay, let's see. So what do I say? At infinity, there is no current in the capacitor, but there is a charge. So let there be charge Q on this. I will take this as plus Q and minus Q. That's what I'm saying. Don't worry like, oh, what will be what? Take it. The science will take care. And what about the current in this branch? The current in this branch is zero. So interestingly, all the current is flowing only in the outer one. So you can clearly see I is equal to V by 3R. Great. Then apply Kirchhoff's law in this loop. You can actually take any loop. I'll start from here. I'll go this way. V minus I capital R. I'm going through opposite to this thing plus I into R. That is anyway 0. I'm going through the battery minus 2V. I'm going to the capacitor minus Q by C. I came back to the battery. This term is 0 because there is nothing there. V minus 2V is minus V. Minus IR will be minus V by 3 minus Q by C. Yeah, I'm getting Q is equal to minus 4 CV by 3. So that means the upper plate is not positive. Bottom plate was positive. That also matters. So I took the upper plate to be positive, but it is saying that is wrong. Easy? Got this? Please check your steps. Yeah, let's see. Great. So that's a bit about a steady state and non-steady state. And the next thing, RC circuit. So we saw what happens at 0 and infinity, but what happens in the middle? So we'll finish our little theory part there. So let's say RC charging circuit. So let's say we have a capacitor, we have a resistor, we have a battery. There is a switch. So like I said, the aeroplane example, right? If you see that, so initially there is no resistance, but as time passes, right, the resistance will increase. That means the current in the resistor will keep changing. So this is a non-steady state. So after time t, this is the circuit how it looks. The charge on the capacitor will be some Q. This would be minus Q, and the current in the circuit is I. And I is equal to dq by dt. So rate of charge on this capacitor is this. Apply Kirchhoff's law. That's always valid. So that would be V minus Q by C minus IR is equal to 0. Remember this. Whenever you see the combination, right, you only have two things. One, Kirchhoff's law, I is dq by dt. There is actually nothing else, meaning mathematically the equations. So this will be CV minus Q by RC is equal to I, and I is nothing but dq by dt. Yeah, this much integration you can handle. So this will be dq by CV minus Q is equal to dt by RC. Integrate this on both sides. This will go from 0 to t. This should be actually Q initial in case the capacitor already has some charge, but here it is 0 to small q. Integrate this. This will be minus ln CV minus Q. Limits will go from Q initial to Q. St by RC. Then you do all the stuff and you end up with Q is equal to CV into 1 e power minus t by RC. If you differentiate this, you'll get current dq by dt. That would be V by R e power minus t by RC. These are standard results, right? Which you should remember, but also remember these are valid only if your initial charge was 0. General exam like CET and bits, they won't do such stuff, but mains may advancement, they can play around. They will say initial charge is not 0. You should be careful with the limits here. Yeah, it is also there for your HSC boards and CBSE boards. So valid if Q initial is 0. Do have a look at this. So Kirchhoff's law and integration. And if you try to plot a graph for this, I'll just write it down again. So Q is equal to CV into 1 e power minus T by RC. So if you plot a Q versus time graph, you can clearly see at T0, your charge was 0. There is a ceiling here, CV. At T infinity, you will reach CV ka value, meaning your graph is increasing like this. You're getting closer and closer to the line, but you'll never reach it technically. So here we define something called a time constant. This is a new word. We call it tau, which is RC. This is 0.63 CV. Again, nothing really special about it. If you put tau is equal to RC, this will become e power minus 1. So the number looks good in the power. So we take it as time constant. So this symbol tau, time constant. If you remember, we also heard about relaxation time. So unfortunately, the symbols all look same. Tau is time constant. This is the time taken to charge the capacitor by 63%. I don't know whether you ever heard this word in phones now. I think few years back, maybe before COVID, they used to have this thing, uh, capacitive charging karke. These Vivo, Oppo phones, na, they used to come with this thing, special capacitive charging. Put the phone and you can charge your 60% phone in 10 minutes. When you're out of charge, you'll get, a boost of charge in 10 minutes or 15 minutes. They used to advertise like this. It's actually called capacitive charging. So if you use a capacitor to charge, I don't know how it really exactly works, but they used to, showcase in that ad like supercharging, something special, big technology. Nothing, it's bullshit. It is actually basic capacitor ka charging. You take a normal capacitor, meaning look at this. To get full, it will take infinite time, but to reach 63%, it takes only R into C, which is actually a very small time. And this is called a time constant. So do remember that. That's one new terminology. Same thing if you try to plot a graph between current versus time. I is equal to V by R into E power minus T by RC. So initially you have actually more current. The current actually decreases as time passes. So here also time constant is defined as 0.37i. So here the current decreases by 63%. So the charge increases by 63, current decreases by 63. Now, again, don't think like, oh, what is this obsession with 63? It's nothing special. E power minus 1, when you take 1 by e ka value, that turns out to be 0.63. So that is a graph for this. All clear with this? The next thing, RC discharging circuit. So in a charging circuit, you put a battery and you increase the charge. In a discharging circuit, there is no battery. Capacitor is already there with a charge. It's getting discharged. So we have a capacitor with a resistor and a switch. So you already have a charge plus Q and minus Q. Again, after time t, let the charge on the capacitor become small q. Let the current be I. Now here you have to be careful. I is minus dq by dt because q is decreasing. If the charge enters a plate, the charge will increase. If the charge leaves a plate, the charge will decrease. Because if you remember the definition of current, it is a rate of flow of charge to a system. If the charge is coming out of the system, you're decreasing. Apply Kirchhoff's law, same story. So this would be minus IR plus Q by C is equal to 0. This would be dq by dt is equal to Q by C. Integrate this. This will go from 0 to t, and the limits will go from q to small q. If you integrate this, you'll end up with q is equal to q into e power minus t by rc. If you differentiate this, you get current is equal to q by rc into e power minus t by rc. These are the formulas for discharging circuit. So discharging, meaning the capacitor is losing, charging or increasing it. If you try to plot a graph for this, the graphs would actually kind of look same. If you would a QT graph and an IT graph, the QT graph would look like this, IT graph also will look like this. They look same. So again, here also you have a time constant RC. So for discharging circuit, you lose 67%, 63%. Yeah, more about this thing you will see there. But if you look at these equations, can you see it looks something like this? If you have done this in your chemistry, look at that formula there. dq by dt is minus q by rc. dq by dt is minus 1 by rc into q. This guy looks like dn by dt is equal to minus lambda n. Can you see this? Chemical kinetics, first order reaction, radioactivity. And what was the result for this? N is equal to n naught into e power minus lambda t. This is the law of radioactivity. So lambda ka place mein we have 1 by rc. Mathematically, they're exactly the same functions. There it is charge, here it is number of atoms. There it is radioactive decay, here it is a capacitor decay. Mathematically, the functions look exactly same. So they can connect stuff and they can play around like that. That's your RC discharging circuit there. Clear with this? Yeah, we will do this in more detail, but this is just a little intro there. Let's do one question, just a basic one based on this. But any doubts on this? And you should be able to integrate this stuff. Let's say we have a capacitor, resistor. Voltage V, this is R1, this is C1, this is R2, and this is C2. So there are two things there. Maybe I'll give you this thing as 2V. So these are two RC charging circuits, okay? This is another really good question. You plot a graph for current versus time graph. And this is how the graph looks like. This is for current I1. This is for I2. So just looking at the graph, can you tell which is bigger? Compare R1, R2. Compare C1, C2. Pretty good mains question. So we have two RC charging circuits. You draw both the graphs. Both are starting from the same point at T0. So looking at this graph, you have to tell which one is bigger. R1 is greater than R2 or C1 greater than C2. Finish off. Last one for the day. Now people got energy. Let's get this. In case you want to see what the RC discharging circuit, here. So it should be V by R e power minus T by RC. Note on the formula if you want for this sake. सम्यक बैटरी सेम नहीं है. बैटरी सेम नहीं है. VN2V. I changed it. It's not VN2V. I'll write it big. They have different batteries, different resistors, different capacitors. Okay, we have few answers. You just have to tell me which one is bigger, which one is smaller, right, Samyak? Yeah, you got the value though, but okay. Okay. I'll give another 30, 40 seconds and I'll show you. Okay, let's see. So what was the logic here? At T0, what happens to a capacitor? It becomes a wire. At T0, capacitor becomes a wire. So initially current will be I1. So you said current is initially same. So that is V by R1 is equal to 2V by R2. So that's the thing. So initial condition you get from there. So R2 by R1 is equal to 2, which is greater than, so definitely R2 is greater than R1. How do you find the time constant? Now, you can actually do this different ways. You can either use slope, but there's a faster way. Look at this thing. So we know the current will drop to 0.37 I in one time constant. Meaning for the green one, time constant is this guy, and for the red one, this is the time constant. Isn't that the definition of a time constant? The time when the current becomes 0.37. You can clearly see tau1 is greater than tau2. So for the first circuit, the time constant is greater than the second circuit, which is R1 C1 greater than R2 C2. But I already know the value between R1 and R2. How much is that? So, so C1 by C2 is greater than R2 by R1, which is 2. So C1 by C2 is greater than 2. So obviously C1 must be greater than C2. All clear with this? You can do that. But if that doesn't click, then what you can do, you can take the current formula. What was current formula? Q by RC e power, in this case, V by R e power minus T by RC. Then you can differentiate dA by dt. And then you see green one has more slope than the red one, isn't it? Then from there, I think you can figure out who has more slope. Yeah, there are ways to do this, but time constant is one good way. All clear with this? There. So that is the thing. Okay, so we did a lot of things today, right? So make sure to go through all the circuits, whatever we did. RC, we have little more. I'll also teach you a way, like without integrating also, you can get the answers. So we will see that all in the next class. I think mostly we should be able to finish off that in maybe first one and a half class. And then we will start off introduction of combination of batteries. What happens if you take multiple batteries, put them in series, parallel, all that stuff. So we are going at a good rate. So you can start solving actually. If you're doing something like HCV or something, I think you can do first 45, 50 questions. So do start solving. Don't wait for the chapter to get over. I think we will take another 3 to 4 classes maximum, because there is one very important part called instruments that will take time. So do start solving. Don't delay it anymore. And okay. And regarding the circuits, right? I'll try to send you a sheet in the class so you can try maybe not many, like 10, 15 circuits, so that you get even more practice. So okay. With that, we'll wrap up for that. We'll continue on Thursday again. So any doubts, anything else, please stay back and ask. I'll be free to leave. So I'll see you on Thursday.